so I want to continue on where I left off yesterday, talking about spherical harmonics. Here, I'll turn on the lights. Okay, so talking about spherical harmonics, right? So here is a Mathematica file that lists a whole bunch of spherical harmonics, just so you know what they look like. Right? So this is in the Mathematica notation. So it's not the standard notation that people write with a paper and pencil, right? With a paper and pencil, people write the y sub L superscript m of theta and phi. And in the Mathematica notation, they made up their own thing, where it's a spherical harmonic y function of 4 arguments. So the first argument is the L number, the second is m, the third is theta, the fourth is phi. Okay? So here is a list of a bunch of the spherical harmonic functions. And what you can see, let's look at a typical one right here. The L equals 2, m equals -2. Okay, so you can see that it has a dependence on theta that is some trig function. And then that's multiplied by a dependence on phi, which is a complex exponential. And in the complex exponential, the thing multiplying phi is the m number. So this is how the m number comes in. It's m times I times phi. Right? So that's the dependence on phi. So it says, as you go around an azimuthal angle, right? Remember, that's what phi means, is the angle going around the z-axis. The spherical harmonic function changes as this complex exponential. And that's multiplied by the theta dependence. And then it's multiplied by some complicated looking coefficient in the front. And the coefficient does the job to make sure that these functions are normalized, right? That is, that if you take one spherical harmonic times the complex conjugate of another spherical harmonic and integrate over all theta and all phi, including the right measure of integration, then you get 1 if the L's are the same and the M's are the same, and you get 0 otherwise. Okay, so here's a list of a whole bunch of these functions. Here, let's check and make sure that the normalization works right. Okay, so if I want, here, I didn't practice this. Let's see if it really works. Okay, so if I want to integrate sine theta, that's the measure of integration, okay? And then let's try this one, okay? So the spherical harmonic 2, 2, okay? So I'll take that times its own conjugate. So the conjugate of 2, 2 times the spherical harmonic 2, 2, and I integrate that for theta from -pi to pi, and I'll integrate that for phi from 0 to 2 pi. This better be 1 or I'll be so embarrassed. Let's see. Oops, no, it's 0. What did I do wrong? What did I do wrong? Oh, it's because theta is not supposed to go from -pi to pi. It's supposed to go from 0 to pi. Ha. Okay. Yes. So that's how you're supposed to integrate. And you remember that everyone knows that the limits of integration for theta are 0 to pi. And everyone knows that the limits of integration for phi are 0 to 2 pi. And you need to include the measure of integration, the sine theta here, or you are guaranteed to get the wrong answer, right? And what if it were not the same spherical harmonic times itself, right? What if we were doing the spherical harmonic 2, 1 times spherical harmonic 2, 2? This better be 0. Phew, okay, good. All right, so that's how these things are orthonormal. And then if we look at a nice plot of each spherical harmonic by itself, you can see something about the shape of the function, how these things depend on theta and phi, that is, on latitude and longitude. So the 0, 0 spherical harmonic, which I didn't save in this plot, okay, that is just a sphere. Okay, what a beautiful sphere. All right, if I plot any of the L equals 1 spherical harmonics, those things are also spheres, but displaced in X or Y or Z. All right, and so here is a displaced sphere. You can see that its center is not at Z equals 0. Its center is shifted up to about Z equals 0.2 or something. All right, yeah, about 0.2. Here is an L equals 1 spherical harmonic, whoops, and it is shifted sideways in X to about X is negative 0.2 in the center. All right. For the L equals 2 spherical harmonics, here are some pictures of those things. All right, so here is a picture of the L equals 2, M equals 0 spherical harmonic. And you can see it has this extended shape with the 2 lobes there on the top and bottom. Here is a picture of the L equals 2, M equals 1 spherical harmonic. And it has this multi-lobe structure in the XZ plane. And then here is the L equals 2, M equals 2 spherical harmonic. And it has this multi-lobe structure in the XY plane. What about L equals 3, right? Well, here's 3, 0. And so, you know, it sticks way up in the plus Z direction, not so much in the negative Z direction. Here is L equals 3, M equals 1, which has more of like a threefold symmetry. Here is L equals 3, M equals 2, which is more like a tetrahedron. Here is L equals 3, M equals 3, and it has this threefold symmetry in the XY plane. Now, all of these plots, I will emphasize, are plots of the real part, right? You get to choose what you want to plot. You can plot the real part, you can plot the imaginary part, you can plot the magnitude squared, right? Just for comparison, this is the real part, this is the imaginary part for L equals 2, M equals 1. And then this is the magnitude squared for L equals 2, M equals 1. Okay, so kind of an hourglass shape. Okay, so I think that's where I left off yesterday, right? So some things you can do with it, right? So one thing you can do with spherical harmonics, right, apart from quantum mechanics, is that spherical harmonics, you know, are ways of characterizing how anything depends on orientation in 3 dimensions, right? So the same way that sines and cosines show how anything depends on orientation just in the 2D plane, going out from the center. The spherical harmonics show all the possible orientation dependencies in 3 dimensions as you vary latitude and longitude. Okay, so just to pick one example of that, okay, suppose you're an astronomer and you discover a new planet or asteroid or something. Okay, and so then you want to tell people what's the shape of your planet. Okay, and so you might say, well, it's mostly a sphere, but it's a little bit distorted from a sphere. So they say, well, how is it distorted from a sphere? Right? And spherical harmonics would be a great way to do that, right? So instead of just trying to make up words and say, well, it's kind of shaped like a pear or something, right? You could describe it quantitatively with spherical harmonics. Okay, so here in this example, so here's a plane sphere. Okay, so it's the 0, 0 spherical harmonic. Okay? And now, what if we wanted to mix in a little bit of the 1, 0 spherical harmonic? Well, this is still a sphere, but it's a sphere that's displaced upwards a little bit. That would not be very useful as a description of a shape, right? Likewise, the 1, 1 spherical harmonic, that just makes the sphere be displaced sideways, okay? But now let's get to something more interesting, okay? What if we have the 0, 0 spherical harmonic plus a little bit of the 2, 0 spherical harmonic, right? In this case, you would say that makes a shape that's extended extra along the z-axis. And so it's a shape that's sort of long and thin, maybe a little bit like an American football, right? Or like a peanut, right? So long and thin, a prolate shape. Likewise, if you go the other way, if you have a negative component of the 2, 0 spherical harmonic, then this makes a shape that's sort of short and fat, right? It's an oblate shape, that's the word for it. And so it's kind of compressed in the z direction, but extending outwards extra in the xy plane. Okay, so what about the 2, 1 or 2, 2? Okay, so the 2, 1 spherical harmonic would make it extended, but not extended towards the North Pole, right? Extended in this sort of diagonal way. And the 2, 2 would make it an extended shape, but extended in the x direction instead of in the z direction. So this is it's a long, narrow shape, right? It's extended in x like that. And then for the L equals 3, M equals 0, right? If you had a little bit of a mixture of that, that makes kind of this pear-shaped planet, right? That's thin in the northern hemisphere and fat in the southern hemisphere. And then here are some other examples, right? Of L equals 3, M equals 1, all right? So this makes this thing with a threefold extension in the XZ plane. Here is 3, 2. So a planet that's shaped a little bit like a tetrahedron, right? And so it has that kind of distortion away from a sphere. And then 3, 3 would have this threefold distortion in the XY plane. And then if you really want to get to something extreme, here I'm jumping ahead to the L equals 10, M equals 0 spherical harmonic, okay? So you can see that has this really high frequency variation, high spatial frequency, right? That it has a lot of peaks and valleys as a function of theta. So that's for L equals 10, M equals 0. For L equals 10, M equals 10, you get this kind of a shape that has a lot of peaks and valleys as a function of longitude rather than latitude. So the general point, I guess, is that when you have a small l and a small m, you have a very gradual variation as a function of orientation on the sphere, latitude and longitude. But if you have a big L or a big M, then it's a much more rapid variation, in and out, in and out. Okay? And so by combining different spherical harmonics, you can get to any variation that you like. Right? And so whatever is the shape of the planet, you could describe it by having a whole series of spherical harmonics. So not just one or two, but a whole bunch of them. And people have actually done this, say, for the shape of the Earth, right? The shape of the Earth is approximately a sphere, but it's not exactly a sphere. And so people have characterized the shape of the Earth in terms of spherical harmonics. And it's not a big distortion like these things I'm illustrating here. It's like a fraction of a percent distortion, but there's a little bit there. When I presented this 2 years ago in this class, one of the students challenged me and said, oh yeah, you think you can describe any shape? How about a cube? Can you make a cube if that's the shape of our planet? So here's the best I can do for making a cube. Whoops, it's not this one, it's 20. Here's the best I could do for making a cube, right? So it depends how many spherical harmonics I want to put into the series, okay? So here is a series where I have the 0, 0, and then I put in a little bit of the 4, 0 and a little bit of the 4, 4. Okay? And it looks kind of like a cube. I mean, you can see it has the symmetry of a cube, but the corners are really rounded off, right? And the edges are really rounded off. And that's because 4 is not a big enough number to represent sharp things like corners, right? So if I wanted to make sharper corners, I have to go to more terms in the series, okay? So here I go up to the same 0, 0, 4, 0, 4, 4. Now I put in a little bit of 6, 0 and a little bit of 6, 4. And it's a little better. It's closer to a cube, right? The corners are getting sharper. Here I go up to 8, right? And so I put in some of 8, 0 and 8, 4 and 8, 8. It's getting closer, right? And so the more terms I put in, the closer I can get to representing sharp features like corners. But I'm never going to be able to have a perfectly sharp corner, right? I would need an infinite number of spherical harmonics to do that. But this is the best I can do for going up to L equals 8 and M equals 8. And so it's not bad, right? So it's, something there, looks like a cube. And we could do similar things with any shape, a pyramid or something else. So that's the story about spherical harmonics, right? And so spherical harmonics are the special functions that are probably the most worth learning of any of the things that I'm going to be presenting this semester. All right, so that's the thing with this visualization. All right, so now let me stop this, and I'm going to go back to how we were in the midst of solving stuff. Okay, so let me go back to the iPad here. I have to share that. All right, share iPad. Here it is. Okay, good. Okay. So let me remind you what we're doing. Let me kind of remind myself what we're doing because I lost track. I was so excited with the beautiful graphics. Okay, what we are doing is solving Schrodinger's equation in spherical coordinates. Okay, so want to solve that in spherical coordinates, which are r, theta, and phi. Okay, and we are doing this if we have a potential energy that only depends on r. That's the kind of situation where spherical coordinates would be really useful. Okay, so that means we have the time-independent Schrodinger equation. Which says that the Hamiltonian acting on psi is equal to the energy times psi. Okay? And it's a psi of r theta phi. And the Hamiltonian is minus h bar squared over 2m times the Laplacian of psi plus v of r times psi. All right, so that's equal to E times psi r theta and phi. Okay, so now, well, yesterday, right, we have this expression for the Laplacian in spherical coordinates. And it's kind of complicated, and I don't want to write it out again. Okay, so we do that, okay? And then we are assuming that psi breaks up into a function of r, which we call big R of little r, times a function of theta and phi. Okay, and then what we did was separation of variables. Okay, so by using this method of separation of variables, our time-independent Schrodinger equation splits into two equations, the radial equation and the angular equation. So to write them out, the radial equation is d by dr of r squared, d big R, d little r, minus 2 times the mass times r squared over h bar squared, v of r minus the energy times the big R function is equal to L times L plus 1 times the big R function. And the angular equation is sine theta d by d theta of sine theta dy d theta plus the second derivative with respect to phi is equal to negative L times L plus 1 sine squared theta times y, theta phi. Okay, so we have these two equations. Okay, and you notice that the constant L appears in both of them. Okay, and so it has to be the same L in both of them. And this symbol, of course, is my handwriting for the cursive letter L. Okay, so we've been working on the angular equation, right? And a nice feature of the angular equation is that it's the same for all potential energy functions. It doesn't involve the potential energy. So we only have to solve the angular equation once. And, well, we've solved it. Well, I didn't really solve it. I told you the solution, okay? And the solution is the spherical harmonic. That is y sub L super m of theta and phi for L is an integer greater than or equal to 0, and m is an integer from minus L to L. Okay, so this is the solution of the angular equation for all such potential energy functions. Okay, so we're done now with the angular equation. We only need to worry about the radial equation, right? That's so we've got the generic solution for the angular equation that works with any potential energy. And now we just need to worry about the radial equation. And we only want to worry about the radial equation in the case where L is an integer, because L has to be an integer here, or there's no global solution, and it has to be the same L. So it has to be an integer there also. Okay, so now we can come back and say, let's solve the radial equation. All right, let's solve the radial equation. Well, the radial equation, as you can see, depends on the potential energy, right? There's a potential energy in there. And so in order to solve the radial equation, we have to pick a potential energy. Okay, so that's just like, you know, what we did before in one dimension, right? Where we had to pick a potential energy for one-dimensional problems, right? And so we got one solution for a particle in a 1D box. And we got another solution for a particle in a harmonic oscillator potential, and another solution for a free particle. Okay, so there's no generic solution for the radial equation. we need to pick a particular potential energy. Okay, so let's do that. Actually, no, I said things out of order. There's one more general thing I want to do before I actually get to pick a particular potential energy. And that is a change of variables, which is kind of conventional. Just let me show you that first, and then I'll pick a potential energy. So here, if we have this radial equation, let me copy it, copy, and I'll paste it here. Okay, whoops, eraser. What people often do is a change of variables. Which is they define a U that's related to the capital R function. It's just little r times the capital R function. So that means that capital R is U divided by little r. And why do they do that? Well, because then there's a little bit of a simplification that comes out. So if you want the first derivative of capital R, you get little r du dr minus u all over r squared, right? That's the formula for the derivative of a ratio. And then that means that r squared derivative of capital R with respect to little r, that's r du dr minus u. And then people say, oh, look, that's what's right here. Okay, and so wouldn't that make kind of a nice simplification? Okay, and so then what? Then if we have in this first term, the first term becomes d by d little r of r little r du d little r minus u. Here we can use the product rule. Here, this is the first times the derivative of the second plus the derivative of the first times the second, and then minus du dr. Oh, cool, those things cancel. Ha, right. So this is equal to just r times the second derivative of u. Okay, and then what? Well, and then if we put that into our equation here, let me copy and paste that again. Lasso. Copy. Paste. Up here, I guess. Okay. All right. So this first term, that's the nice thing with the u. So the first term gives us just r times the second derivative of u. And then what? The second term gives us 2m r squared over h bar squared. We have this potential energy. But anyway, there's a u over r, because that's what capital R is. It's u over little r. And likewise, over on the right side of the equation, there is a u over little r also. And now let's divide every term here by little r. Is that what I want? Yeah, okay. Let's divide every term here by little r. Okay, so now this equation reduces to, let's see, this second derivative minus 2m over h bar squared like that. All right, and then what? Then if we multiply through everything by negative h bar squared over 2m, we have a second derivative like this, minus v of r times u minus plus e times u. No, this is a plus. This is a minus. Oops. Minus e times u is equal to negative h bar squared over 2m L times L plus 1 over squared. Okay, and then if I do just one more step, let's put the L plus 1 term on the right side, no, on the left side of the equation. So we have v of r plus this thing over r squared. All of this times u is equal to energy times u. Okay, so why did we do this? Well, the reason is that this equation in the end, it looks like the one-dimensional time independent Schrodinger equation, right? That is, it has a regular second derivative term over there, and it has just the energy times function over there, and it has some function of r times the thing we're looking for right here, okay? So it looks as if it's the regular one-dimensional equation that we're sort of used to with an effective potential. So with an effective potential, which is the effective of R is the regular potential plus some h bar squared L plus 1 over 2m r squared. Okay, so for those of you who remember your classical mechanics, which hopefully includes Andrew because he learned it from me, right? For those of you who remember your classical mechanics, you might remember at some point solving equations of motion, classical equations of motion, say for a planet moving around the sun, right? And when you do that, you know, in typically people say, let's assume the planet has a certain amount of angular momentum as it moves around the sun. And then at least one solution method says, well, there's an effective potential for the planet moving around the sun with a certain angular momentum. And that angular momentum makes an effective correction to the potential energy, which is a centrifugal term that looks as if it is pushing the planet away from the sun, right? It's kind of like the centrifugal force effect, right? And so that's what this is, right? So this is a centrifugal term, which is related to angular momentum. And indeed, we're going to be getting to angular momentum in a few days. And so this is sort of a preview of that point, right? That the L quantum number, you can remember, is related to angular momentum. And it's doing the same kind of thing here in the radio equation as you might be accustomed to in classical mechanics. Okay, but in any case, now, what if we actually want to solve this thing? Okay, so suppose we want to solve the equation. I need to make some assumption for the potential energy, right? I mean, here's an equation that has the potential energy. I can't solve it for arbitrary potential energy. I have to make some particular assumption. Okay, so in one dimension, the first thing that we tried was a particle in a 1D box, right? And then I showed you a 3D box. What about if we had a particle in a sphere? All right, so let's say for an example, let's do a particle in a sphere. So that means that the particle is confined inside some sphere like this, let's say with a radius of little a, and it cannot possibly get out. Okay, so it's a spherical container instead of a rectangular container for the particle. So that means that the potential energy is equal to 0 if R is less than or equal to A, and it goes to infinity if R is greater than A. So this is a potential energy which confines the particle in the sphere so the particle cannot possibly get out. So this is certainly analogous to a particle in a rectangular box, but it's a sphere instead of a rectangular box. Okay. So if we want to solve this, our solution has to be something that works for 0 potential energy inside the sphere, and then the solution has to go to 0 right at the edge of the sphere. Right on the surface, the wave function has to go to 0. Okay, so that means then, here, let's write it out. Okay, so inside the sphere, we have the equation with no potential energy. So this d2u dr squared plus the centrifugal term, L plus 1 over 2mr squared, u is equal to E times u. And then there's a boundary condition that u of r equals 0 at r equals a. Okay, so how do we solve this thing, right? Well, there's one case in which it's easy, right? It's easy in the case where L equals 0. right? And so in the case where L equals 0, where we don't have this term, then there's a second derivative, is a constant times the function. We've done that lots of times, right? We know how to solve that. The solutions are sines and cosines. Okay, so I can at least write that one out. So we'll say let E equal h bar squared k squared over 2m. So that means then that if L equals 0, then negative h bar squared over 2m, the second derivative, is equal to k squared over 2m times u. So the h bar squareds and 2m's cancel, right? That the second derivative is just minus k squared times u. You know all about that problem, right? And so you know that u as a function of r could be something times the sine of kr plus another coefficient times the cosine of kr. So the function big R of little r, that's, remember, u divided by little r. So that is a sine kr over little r plus b cosine kr over little r. Okay, so we have these two arbitrary coefficients. We could say, what happens when little r goes to 0? So right at the center of the sphere. So at the center, where little r goes to 0, the first term is actually okay, because the sine of kr in the numerator goes to 0, and the little r in the denominator goes to 0, and the ratio of those things is nice and well behaved. The second term, though, that's no good, because here the numerator goes to b, but the denominator goes to 0. See, it blows up. So that's a good reason why we better not have a b term. We better just stick with the a term. Okay, and then what? So at the surface, where r equals a, we have a boundary condition that the function has to go to 0. All right, so a, big A times the sine of k times little a has to be 0. So this is kind of just like a particle in a one-dimensional box, right? And so we say, well, either the amplitude A equals 0 or the sine of k times little a equals 0. But if capital A is 0, there is no wave function. So that's no good. So we better have that the sine of k times little a is 0, which means that k times little a has to be an integer. Well, I'll give it a name. It has to be an integer n times pi, right? Where this capital N is an integer. All right, so k has to be an integer times n, an integer n times pi divided by the radius. Okay, and so that means we know the wave function. We also know the energy, right? That the energy then is h bar squared, k squared over 2m. So h bar squared, big N squared, pi squared over 2m, a squared. Okay, so this is okay if L equals 0, right? So we know now some of the special separable solutions. We know the special separable solutions if L equals 0. But now you're wondering, well, what if L is not equal to 0? Because we know that the number L can be any integer greater than or equal to 0. Okay, so what if L is greater than 0? Oh man, this is where we have to get into more special functions. And these are not super interesting special functions, but I'll just tell you the answer, okay? The answer is that U of R can be one coefficient times R times the J sub L special function of KR plus another coefficient times R times the N sub L special function of KR. And these functions have names. The J sub L is called the spherical Bessel function. And the N sub L is called the spherical Neumann function. Okay, so various people in history have studied different functions and stuck their names on them, right? Unfortunately, there isn't a Selinger function yet, but I'm still working on it. So these functions, you know, there's all kinds of data about these functions that's out there, and it's not my favorite thing to teach. So, you know, I promised you that the spherical harmonics are the important ones. And so, you know, learn about those. But these things are not maybe as high a priority. The main thing I can tell you is that the Neumann functions, they also blow up at the origin. At the center of the sphere. So those are no good. So the solution, it has to be one of these spherical Bessel functions. Okay? And luckily, Mathematica knows stuff about spherical Bessel functions. It's built into Mathematica. So let's switch back to Mathematica, and I will show you what a spherical Bessel function looks like. Okay, so we gotta stop the sharing and switch. Okay, so I made Mathematica plots of these guys. Okay. Share Mathematica here. Okay. So very conveniently, Mathematica has a spherical Bessel function command, okay? And so for the spherical Bessel function, J sub L as a function of X, the command is spherical Bessel J, and then you put in the L, and then you put in the X. Fair enough. So here's a plot of the spherical Bessel function J0. This function is actually equal to the sine of X divided by X. So this is actually a very nice convenient thing that's just like what we calculated before. Here is the J1. It oscillates up and down, but they all oscillate up and down. Here's the J1, here's the J2, here's the J3, for whatever it's worth, okay? So these are functions that are knowable, plottable functions, right? And you can see they each have a set of places where they are equal to 0, right? Each of them crosses 0 at a certain set of positions, right? But these positions are not just multiples of pi, except in the 0th case. In the 0th case, they are multiples of pi. It crosses 0 at pi, 2 pi, 3 pi, 4 pi, right? Nice multiples of pi. But in all the other cases, it does not cross 0 at multiples of pi. It crosses 0 at certain weird points that are not multiples of each other. Now, suppose L equals 1, right? So we're working with this function right here, okay? We want to say we have a boundary condition right at the surface of the sphere. Okay? So that means the surface of the sphere, it could be at this point where the function goes to 0, or it could be at this point, or this point, or this point, right? So there's a certain series of allowed solutions corresponding to the size of the sphere, but those allowed solutions are not regularly spaced values of k. What they are is, oh, darn, I gotta switch back to the iPad for a minute. Okay, I'll do it. How do I do it? Stop. Okay, so if we want the boundary condition at r equals the radius of the sphere, okay, that means we must have JL of KA equals 0. That is, when you plug KA into the Bessel, the spherical Bessel function J sub L, you have to get 0. Okay, we want to solve this for K. How do we do that? Well, we say KA has to be equal to a certain place where the Bessel function crosses 0. That gets a name. It is called beta sub NL, where this thing is the nth 0 of the Lth spherical Bessel function. So any of the spherical Bessel functions crosses 0 at a whole series of places, not regular, but a series of places. And so you could say, if I'm looking at Bessel function number L, I look at for the nth place where it crosses 0. That's a certain number. And then K is 1 over the radius times that place. And then the energy is h bar squared k squared over 2m a squared times that special number squared. Luckily, Mathematica also knows about these things. Where does the Lth Bessel function cross zero? The spherical Bessel function. If I just say Bessel function by itself, that's a different thing. So it's the Lth spherical Bessel function. Okay, so let me go back to Mathematica, and I can do that real quick. Okay, so I didn't even know that this was in Mathematica until last night, and then I found it from a guy on the internet. Okay, so from a guy on the internet, I downloaded this nice command to find what is the nth place where the Lth Bessel function crosses zero. Okay, what a handy command. Okay, so the first place where Bessel function number 3 crosses zero is supposed to be 6.98. Ooh, look here. It's crossing zero at 6.98. Okay. The second place where it crosses zero is 10.41. Yep, that's it, 10.41. The third place is 13.698. Okay, here, 13.698. Okay, so this command actually works. All right, based on this, we can actually put together all the pieces and get any solution for a particle in a sphere. Let's do it in some examples. I just did this last night. I'm so excited. Okay, let me show you. Here's an example of a full solution, right? So for a full solution, I need to specify 3 numbers. I need to specify the L and M that go with the spherical harmonic. And then I need to specify the integer n that says, well, which of the 0 crossings am I caring about? Okay, so let's pick an example. Suppose L equals 0 and M equals 0 in the spherical harmonic. And I'll think about the first 0 crossing. Okay? So I'll make an example with certain set of parameters for n, L, M, and then for the radius and the mass and h bar. Okay. So then the corresponding beta is the first place where the 0th spherical Bessel function crosses 0. That is in fact pi. Okay, so here's a number pi. So the R function then is an arbitrary coefficient times the spherical Bessel function with L equals 0 evaluated at beta times R over the radius. Okay. So that is a function which looks like this. Okay, this is a plot of capital R as a function of little r going out to the radius of a sphere. Okay, and you can see it reaches 0 just when little r reaches the radius of a sphere. I am multiplying that by the appropriate spherical harmonic. Okay, so the spherical harmonic with L equals 0, M equals 0. That gives us our solution. Okay, so this thing is supposed to be a solution of the Schrödinger equation. Let's check. Is it really a solution of the Schrödinger equation, or did I mess up? All right, so let's do that. Okay, so in the Schrödinger equation, inside the sphere, where the potential energy is 0, okay, we just would say, minus h bar squared over 2 times the mass times the Laplacian of psi should be equal to an energy times psi. Okay? So here, this is minus h bar squared over 2 mass. Here's the Laplacian I have to tell Mathematica, do the Laplacian in spherical coordinates. And then if I divide that by psi, I get all this stuff, which is supposed to be a constant. It's supposed to be the energy, actually. Is this thing really a constant? Well, let's check. I'll make a plot of it. Yeah, actually, it is a constant, okay? So Mathematica didn't simplify it to be a constant, but yeah, actually it comes out to be a constant. And if I compare that with what the energy is supposed to be, that's h bar squared over 2 times the mass, a squared times this beta, that energy is supposed to come out to be 4.93 in these units. Ooh, look, 4.93, that's just about right. Okay, so it really is a solution of Schrödinger's equation. Cool. Now let's normalize it, okay? So we have psi star. I can check the normalization by integrating psi times psi star over r goes from 0 to little a, and theta goes from 0 to pi, and phi goes from 0 to 2 pi. So if I do that integral with the right measure of integration, the r squared sine theta, better not forget that. Okay, so it's something times the absolute value of a squared. You've seen lots of problems like that in this semester, right? So you pick a value of a so that that integral comes out to be 1. Okay, so a better be 4.44. All right, here is a normalized solution that goes with n equals 1, L equals 0, and m equals 0. Here is the corresponding probability density. What if I want to plot it? How do you plot something in 3 dimensions? Well, you can make a contour plot, right? So I make a contour plot in 3D of all the places where the wave function equals 0.2. That's a sphere. It's a sphere inside our main sphere. Right? Our main sphere has a radius of 1. This is like a little sphere of radius 0.7 or something. Right? And likewise, the probability density is spherically symmetrical. That is a simple example. What about a more interesting example? Okay. Oh, before I go on, I should point out a weird thing about notation. You should be alert for the fact the letter M now means 2 things, right? There is a M that goes in the spherical harmonic, the YLM. There is also an M that's the mass. These 2 M's have nothing to do with each other, right? They're just, somehow we have the letter M that conventionally means mass, and it conventionally means the quantum number in the spherical harmonic. When I was a student, the first time I saw that, I thought that was the funniest thing I'd ever seen, right? My professor wrote down an equation that had an m divided by m, and they didn't cancel because they were 2 different m's, and I just laughed my head off. Now that I'm a professor, I don't think it's funny anymore. I just think, you know, of course, obviously this m is one thing. Obviously that m is another thing. So in this Mathematica file, I write out the word mass to mean mass, and the other m is the integer m. Okay, more interesting example. What if we go to L equals 1 and m equals 0? And I'll still look for the first solution, n equals 1, okay? It still satisfies Schrödinger's equation. You can read the Mathematica code, or you can take my word for it, right? But it all works. I can normalize it again. Here now is the contour plot, okay? So here is a contour plot where the blue contour means where the wave function is negative real, and the orange contour means where the wave function is positive real. And so these are contours of the wave function. These are contours of the probability density. So the probability density is not spherically symmetrical. The probability density has these lobes, a positive z and negative z. That's where there's a big probability of finding a particle, not everywhere else in the sphere. What about n equals 1, L equals 1, m equals 1, right? So the 1, 1 spherical harmonic. Okay, so here now are the two lobes in the real part of psi. Okay, so here positive x is where psi is positive real. Negative x is where psi is negative real. Now here's the imaginary part of the wave function. This positive y is where psi is positive imaginary. Negative y is where psi is negative imaginary. So the probability density looks like this. Like the probability density is spread out in the xy plane like this. Let's keep going. Okay, I got so excited about this. I did a whole bunch of these. So here is L equals 2, M equals 0. Okay, so here for the wave function, you can see it's positive real around this belt around the center, and it's negative real at big positive and negative z. So the probability density looks like this one. Okay. And we can keep going, right? So this is an automatic way of generating solutions and seeing where is the wave function, positive or negative real, or positive or negative imaginary, or where there's a big probability. Okay, so here's an example where you have the lobes arranged differently. And I'm running out of time, so I'll skip ahead to an L equals 2. Well, so this one is L equals 2, M equals 2, and N equals 1. Okay, so here we have a certain angular dependence that comes from the L and M, and then it has a certain radial dependence that comes from the function of R. Okay, what if I go to change the N number? The N number, so I'll go to N equals 2. Okay, so that is the second place where the spherical Bessel function is equal to 0. In that case, if I skip ahead to the probability density, now it has the same kind of angular dependence, but it has a different radial dependence. You can see it has this like extra variation as a function of R, as an extra max and min as a function of R before you get out to the edge of the sphere. Now, have any of you, by any chance, seen plots like this, either in a modern physics class or maybe in a chemistry class? Right? Where have you seen plots like this before, anybody?
Orbitals.
For orbitals, yes. So this is the beginning of the idea of an orbital, right? So these are orbitals for a particle in a sphere, right? So it's not an electron feeling a Coulomb attraction to a proton. It's instead an electron that's confined inside the hard walls of a sphere. But it's still the same idea of orbitals, right? So it's the same idea of how a wave function can depend on radius and on the two angles. And it's characterized by three quantum numbers, the same way orbitals are, right? That there's an N and an L and an M, same as you've seen with orbitals. And the L and the M are the same kind of thing. The N is something a little bit different because it's a different potential energy. But this is the beginning of the idea of an orbital for a hydrogen atom. Okay. And so indeed, the next thing we're going to do will be to change the potential energy and make it the Coulomb potential energy to describe a hydrogen atom. Okay, so that's what's coming up, all right? So with the particle in a sphere, let me just say one thing briefly. For the particle in a sphere, what I really wanted to do was to start making movies of like playing Pac-Man, not Pac-Man, Pong inside a sphere, right? Where the probability would be oscillating around for different parts of the sphere. I have not yet been able to do that just because this code is too slow. The code that I have needs a few minutes to generate each frame. So that's why I haven't been generating them live. I've just been showing you things that are pre-calculated. So I would like eventually to be able to scale this up and make movies of the probability sort of oozing around inside a sphere. I haven't quite gotten to that yet. Maybe I'll get that by Thursday, maybe not. But if not, then I'll just go directly to the hydrogen atom then. Okay, I'm over time, I'm sorry. I'll stop talking and I will see you guys on Thursday. Okay, so on.